Imagine writing just a perfectly grammatically correct sentence. I mean, the vocabulary is precise, the syntax is absolutely flawless.
Right, it conveys the information with basically mathematical efficiency.
Exactly. But the catch is that it's so perfectly efficient, like so completely devoid of human context, that the person reading it has to sit and stare at it for 5 minutes just to decipher what you actually meant.
Oh yeah, it happens constantly. And, not just in software.
Right.
You see this in legal contracts, in academic papers, anywhere that prioritizing structural perfection ends up, well, stripping away the very context that makes the information digestible for a normal human being.
And that tension is exactly where we are heading today. Welcome to the deep dive. We have a really highly specific mission for you today.
We do.
We are going to be peering directly over the shoulder of a programmer working in the trenches. They're navigating the complex architecture of Haskell.
Which is notorious for this exact issue.
Yeah, exactly. And we are going to explore the fascinating and honestly often frustrating tug of war between writing code that the machine considers flawless and writing code that a human being considers readable.
It is a dilemma that, every developer eventually faces,
Yeah.
especially in languages with strong functional paradigms where the compiler is just constantly pushing you toward that mathematical purity.
So our guide for this exploration is a blog post. It was published yesterday, July 7th, 2026, by a developer named Ang.
Right, and the title really sets the stage immediately.
It does. It's titled Notes-on-Haskell-Programming, Part 180, Transitioning to Data.Bitfunctor.bimap.
A very technical title.
Very. But okay, let's unpack this. Because what looks on the surface like a highly specialized tutorial about refactoring Haskell code actually contains this massive universal lesson.
A lesson about how tools that are meant to optimize our workflows can actually trick us into communicating in ways that isolate us.
Right. Automated linters and these refactoring tools, they're brilliant at finding inefficiencies. But, well, they lack empathy.
Yeah, they don't know who is going to be reading the repository at 3.0 a.m. 3 years from now.
Exactly.
They only know what the abstract syntax tree dictates is the absolute most optimal transformation.
Which perfectly brings us to the context of Ang's post. Before we look at the specific code transformation, we need to understand the environment that triggered it in the first place.
Right. The setup is crucial here.
Yeah, so Ang is deep into some feature work. They are building out something related to an input text file, so they're likely handling some parsing or text conversion stuff.
Standard day-to-day developer work.
Right. But midstream, just completely by coincidence, Ang decides to run a tool called Hlint against the code base.
And for anyone who hasn't spent time in the Haskell ecosystem, Hlint is basically the standard code linter.
Like a superpowered spell checker for code, right?
Basically, yeah. It
Yeah.
parses your source files, and it suggests changes to make the code simpler, cleaner, or more idiomatic.
Right.
Developers will often use it as a sort of automated mentor to catch boilerplate or stylistic missteps.
And I mean, the allure of that automated cleanup is incredibly strong. You just want to click a button and have it fix everything.
Oh, absolutely. It's very satisfying.
So Ang actually completely pauses the feature work, the text file feature, to investigate Hlint's suggestions. But here is the snag.
And it's a very familiar one if you've ever dealt with dependency management.
Oh, man, yeah. So Ang wants to apply these refactoring suggestions automatically, but the tool won't let them.
Of course not.
Right. The package responsible for making those automatic changes, which is called apply-refact, it throws a versioning error.
Ah, the classic dependency nightmare.
It doesn't support the compiler version Ang is running, which is GHC 9.1.x, nor does it align with the corresponding stack LTS snapshot.
Right, so that is the classic trap of the modern development pipeline. You bring in a tool to save you time.
But the tool is broken.
Exactly. Because the underlying infrastructure has shifted. In this specific case, the Glasgow Haskell compiler updated to the 9.n branch. And that likely altered the abstract syntax tree that apply-refact relies on, so the automation just breaks.
I mean, it's like deciding you're going to fix a wobbly table leg, right?
Okay, I like this.
And you find this fancy new power tool in the garage to do it, but then you realize the battery is completely dead.
And you don't have the charger.
Exactly. You don't have the charger, so you end up just manually rebuilding the whole dining set with a hand screwdriver anyway. And it takes twice as long.
What's fascinating here is the psychological pivot. Because most developers might just abandon the tool at that point. Just go back to the feature work.
Cut your losses.
Right. But the desire to optimize, That knowledge that there is quote-unquote better code hiding in the file, it's just too strong.
You can't unsee it.
Exactly. So Ang actually commits to resolving Hlint's suggestions manually, line by line.
Rebuilding the table by hand. So let's actually look at the very first refactoring suggestion that Hlint provides, because it gives us this perfect microscopic view of this tension between the human and the machine.
And this happens in the file src_access_to_ebookconverter.hs, right?
Yes, right at line 143. So Ang had written this standard lambda function. It takes a pair of inputs S and D,
Okay.
and it applies the tpack command to each of them separately, and then it returns the newly packed pair. The code is literally just a \, /, S, D, close paren, arrow, open paren, tpack S, tpack D, close paren.
Right. And contextually, tpack is being used here to convert standard strings into data text.
Which is important for performance, right?
Very. Strings in Haskell are literally just linked lists of characters. They are notoriously memory-heavy and slow for heavy processing.
Right, so converting them to strict text is just standard practice.
Exactly. So Ang is taking this lambda function and mapping it over a structure called single width to double width.
And that generates a collection called tidy pairs.
Yes. And those tidy pairs are then used downstream for a text replacement operation using treplace.
Okay, so that makes perfect sense for the feature. The developer just wants to ensure all the text inputs are efficiently packed before replacing the strings.
Right. It's completely explicit. You can look at the lambda function and clearly see the variables.
You literally see S and D being grabbed, processed, and returned.
Yeah.
But Hlint flags this. It essentially tells Ang, look, you are writing too much code.
It wants to reduce the boilerplate.
Exactly. Instead of that explicit lambda function, Hlint suggests using Data.Bifunctor.bimap tpack.
Which is a significant structural reduction.
Oh, huge. And according to Ang, both versions achieve the exact same mechanical result.
Right, the output is identical.
But Hlint prioritizes the bimap version specifically because it reduces that boilerplate. So rather than having to manually declare the variables, map over the first one, then map over the second one, bmap, just handles the underlying structure for you.
It really is elegant from a mathematical standpoint.
It is. Like, going to a real-world translation here. Tell me if this tracks.
Okay, let's hear it.
Is the original code kind of like a recipe saying, take the salt, take the pepper, put the salt in a shaker, put the pepper in a shaker?
Yes, very procedural.
And bimap is just saying, shakerize both.
That's actually an excellent way to visualize a bifunctor.
Shakerize both.
Yeah, in Haskell, a functor is a structure that you can map a function over like a list.
Right.
A bifunctor is a structure that has two distinct type parameters, like a tuple or an either type.
Okay.
So by using bimap, you are basically telling the compiler, look, I have a function for the left side and a function for the right side. Just apply them simultaneously.
So you don't need to manually unpack the tuple.
Nope. You don't unpack it, apply the functions, and repack it. The bimap abstraction just handles all the mechanics for you.
Which eliminates all that repetitive boilerplate. And honestly, I understand why developers are so focused on eliminating it.
Oh, it's a huge deal.
Yeah, when you're scanning hundreds of lines of code, repetitive structural commands just create a ton of visual noise.
They do. They obscure the actual business logic.
Right.
If a developer has to read through 5 lines of manual tuple unpacking just to realize you are simply converting strings to text, I mean, that's wasted cognitive load.
Yeah, bimap collapses all that mechanical noise into a single, elegant command.
But, and this is key, reducing visual clutter isn't the only reason Hlint suggests this change.
No, it's not.
No.
And this is where we get into the hidden mechanics of Haskell, which is wild to me. The tool explicitly notes that using DIMAP, and this is a direct quote from the tool, increases laziness.
Ah, yes. Laziness.
Now wait. In the real world, in almost any other engineering discipline, being lazy gets you fired.
Usually, yes.
You want the system to do the work as fast as possible to get it out of the way. If you're building a bridge, you don't wait to pour the concrete until the first car drives over it.
That would be a disaster.
Right. So why does the Haskell compiler actively reward procrastination? Why is increasing laziness a badge of honor here?
It goes completely against our intuition of how physical work is done, certainly.
Yeah.
But in computer science, specifically in pure functional programming, laziness, or what we call deferred evaluation, is actually a massive architectural advantage.
Okay. How?
Well, when Hlint says this increases laziness, it means the code is structurally designed to avoid computing those tpack conversions until the absolute last possible microsecond.
But how does that actually work in memory, though? Like, if it's not doing the conversion immediately, what is it doing?
So instead of immediately calculating the value, the compiler creates what we call a thunk.
A thunk.
Yeah, Thunk. You can think of a thunk as an IOU.
Oh, I like that.
It's this tiny little wrapper in memory that says, I promise to evaluate this function and produce this value, but only if you explicitly demand it later.
Okay, so it's a placeholder.
Exactly.
Mm.
In eager languages like Python or Java, the system evaluates arguments before it applies the function.
It just does the work up front.
Right. It allocates the memory, processes the strings, regardless of whether you end up using all that data or not.
So if Aang's tidy pairs contained, like, 1,000 strings,
An eager language would process all 1,000 immediately.
but if the downstream tReplace function only ended up needing the first 10 pairs before exiting,
Then the system just wasted time in memory processing the other 990.
wow. Okay, so lazy evaluation prevents the system from doing unnecessary math.
Exactly. By moving to BIMAP, Hlint is optimizing the way those IOUs, those thunks, are constructed. It aligns the code closer to Haskell's natural execution model.
That makes total sense. And Aang also notes in the post that BIMAP represents the, quote, idiomatic Haskell approach.
Yes, the cultural dialect of the language.
Right.
Every programming language has idioms. You can write perfectly functional code that solves the problem, but if you don't use the native idioms, you sound like a tourist reading from a phrasebook.
So to a native Haskell developer, manually unpacking a tuple with a lambda function is, what, structurally loud?
Yes. It's clunky. BIMAP is just the culturally fluent way to express that specific operation.
So looking at the scoreboard here, we have a solution that removes visual clutter, right?
Right.
It optimizes memory allocation through lazy evaluation,
Yes.
and it aligns with the cultural standards of the language community. It seems like Hlint is completely undeniably correct.
It does seem that way.
But this brings us to Aang's crucial realization, which is really the pivot point of this entire deep dive. Because optimizing for the machine and optimizing for the community idioms, it comes with a cost.
The readability trap.
Yes, the readability trap. Because Aang points out a massive caveat here. BIMAP fundamentally relies on point-free style coding.
Right, which changes the visual landscape of the code entirely.
Exactly. By implementing this tool's suggestion, those explicit variables, the ets and the day from the original lambda function, they are completely removed from the code. The points of data just vanish, and only the functions remain.
And this is a concept rooted deeply in combinatory logic. In point-free style, which is also known as passive programming, the code specifies the operations to be performed, but it never explicitly names the arguments.
The arguments being the data itself.
Right. The data just implicitly flows through the composition of the functions.
And Aang explicitly states that while this style undeniably improves code cleanliness, it introduces a really severe penalty.
Which is?
If a developer isn't heavily experienced with point-free style, this change may actually reduce the readability of the code.
Ah, yes.
So what does this all mean? If the linter is pushing for an optimization that drops the variables and makes the data flow basically invisible to, say, a junior developer, shouldn't we push back? I mean, shouldn't the ultimate goal of the code base be human readability?
That is the eternal debate.
Is it?
Oh, absolutely. And frankly, the answer isn't always yes.
Wait, really?
Yeah. I mean, if you are writing a high-frequency trading algorithm or a core system scheduler, the ultimate goal is raw execution speed.
Okay.
The compiler's preference reigns supreme in those cases, and human readability takes a backseat. But for the vast majority of software,
Code is read by humans far more often than it is written.
exactly, and that human needs context. When you look at an explicit lambda function, you instantly see the number of arguments.
You see the S, you see the D.
Right. Your brain can immediately map those variables to the domain logic. But when you look at BIMAP T.Pack, TPack,
You have to mentally unpack the Bifunctor type class yourself.
yes, you have to already know the shape of the data flowing into it. Point-free style is incredibly mathematically elegant, but it requires the reader to hold a massive amount of structural context in their head just to read a single line of code.
It's like reading a novel where all the pronouns have been removed.
That's a great comparison.
Right, like you just have to intuitively track who is speaking based purely on the verbs.
It's technically possible, but it is exhausting.
Totally exhausting. And what really strikes me about Eng's blog post is the maturity of the reflection here.
As
Well, a less experienced programmer might have just blindly accepted the Hlint suggestion, right? Just to get a perfect score.
Oh, definitely. Chasing that perfect score from the automated linter is a very real trap.
Right. Satisfied that they achieved a quote-unquote cleaner architecture according to the machine. But Eng actually pauses the refactor to weigh the structural optimization against the cognitive load it places on the next human to touch the file.
Eng recognizes that clean code, defined by a lack of boilerplate and pure mathematical efficiency, is not inherently clear code.
Exactly.
It really demonstrates a high level of engineering empathy.
I love that phrase, engineering empathy.
Yeah, because when we adopt tools like Hlint, we are essentially outsourcing our stylistic decisions to an algorithm that values mathematical reduction over narrative clarity.
And knowing when to reject or, question that algorithmic preference is what separates just a typist from a software engineer.
Perfectly said.
Which beautifully summarizes the journey we've taken through this single blog post. Let's quickly recap for you, the listener, what we've actually unpacked today.
We started by looking over Eng's shoulder during what seemed like a mundane feature build.
Right, working on a text input file, only to watch that workflow get completely hijacked by the allure of an automated linting tool.
A tool that, ironically, couldn't actually automate anything because of those mismatched GHC and stack LTS versions.
Right, forcing that manual line-by-line confrontation with the code structure, rebuilding the table by hand.
And that forced manual labor is what allowed us to examine the shift from a highly explicit lambda function to the optimized point-free Data.Bifunctor.bimap.
Right. We explored how that transformation satisfies the compiler's desire for deferred, lazy evaluation, creating those little IOU thunks.
And how it aligns with Haskell's native cultural idioms.
But most importantly, we uncovered the hidden cost of that mathematical elegance.
The erasure of explicit variables.
Yes, which actively degrades readability for anyone not totally fluent in that specific architectural style.
It really just proves that optimization is always a trade-off. You are always borrowing clarity from one domain to pay for efficiency in another.
Exactly. And the implications of this trade-off, they extend far beyond the Haskell ecosystem.
Oh, everywhere.
Yeah. Whether you are writing code or drafting a legal document or publishing an academic paper, you are constantly negotiating this exact same tension.
The parallels to professional jargon are just undeniable.
They really are. Think about it. When a lawyer drafts a contract using really dense, highly specific legal terminology, they are essentially writing point-free code.
That's entirely accurate. To another lawyer or to a judge, that terminology is a bifunctor.
Right. It is incredibly efficient. It bypasses the boilerplate of plain English and communicates highly complex structural logic in just a few words.
It is culturally idiomatic within the legal system.
But to you, the client who actually has to sign that contract, the explicit variables have vanished.
The human context is completely gone.
Exactly. The document is perfectly optimized for the legal compiler, but it is completely unreadable to the human user.
And the mark of mastery, whether you're in software engineering or law or academia, isn't just knowing how to write the most complex, optimized language possible.
Wow.
It's knowing when to abandon that optimization.
Yeah, it's knowing when to deliberately write the quote-unquote inefficient lambda function, leaving those explicit variables right there on the page, simply because you know it will save another human being from confusion down the line.
It's choosing empathy over elegance.
Which leaves us with a final thought to consider as we wrap up this deep dive. We've seen how Eng navigated the specific dilemma today, weighing Hlint's mathematical perfection against human readability.
The very human choice.
Right. But look at the broader trajectory of our tools right now. Every single day, linters, static analyzers, and now AI coding assistants are actively training developers to write language that prioritizes machine-readable efficiency.
They structurally reward those point-free styles.
Yep. Exactly. They reward the abstractions, the removal of quote-unquote human noise.
They are slowly shifting the actual dialect of our systems.
So the question you really have to ask yourself is this. If our automated tools are relentlessly shaping our communication to be leaner, faster, and more abstract, are we slowly designing a future where humans are no longer the primary audience for the things we write?
That is a fascinating question.
Keep an eye out for who the blueprint is actually serving. Thanks for joining us on this deep dive.